Right, so we're back and we're doing geometric series, sum to infinity. Somebody said they wanted music, right? Well, there it was. It wasn't you, was it? Okay, so Sn equals a1 minus r to the n over 1 minus r. What? That's the formula that we just looked at yesterday. And now what we're looking at is, what is the sum of infinite number of terms? Now, like, what's going on here? So if we've got some sort of series and a geometric series, let's say we've got something that like starts at 1 and doubles. 1 plus 2 plus 4 plus 8 plus... Well, if we keep doing this like infinite times forever and ever, well, not infinite, but like the concept of infinity is quite a difficult one. If we keep kind of going forever and ever, well, isn't that just going to like keep getting bigger and bigger? And like 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 16 is 31. So clearly, sum to infinity for this one, like it's just going to keep getting bigger. So that doesn't look like it's always going to work so nicely. What about like, let's take something and multiply it by, say, like -2 or something. So like 1 minus 2, so we're multiplying by -2 now, plus 4 minus 8 plus 16. Well, 1 minus 2, that's -1, plus 4 is 3. Let's just keep track of this. Minus 8 is -5, plus 50, plus 16, 11. Also looks like it's getting like to these bigger and smaller numbers, right? So that doesn't look like it's going to be much good either. But wait, let's try something that might work a bit better. What happens if we had a sequence that went like 8 plus 4 plus 2 plus 1 plus a half plus a quarter, so it was like halving each time? Well, 8 plus 4 is 12. 12 plus 2 is 14, plus 1 is 15, 15 and a half, 15,75. This one feels like it's getting like closer and closer and closer to 16, I guess, right? Like it feels like it's getting closer. So our ratio for this one was 2. Our ratio for this one was -2, but our ratio for this one is a half. And just to be complete, if we had a ratio of -1/2, and we had 8 minus 4 plus 2 minus 1 plus a half minus a quarter, that also has the same kind of feeling. 8 minus 4 is 4, plus 2 is 6, minus 1 is 5, plus a half is 5.5, 5 and a quarter. Also feels like it's getting closer to a number. It's converging. So let's just add our plus feathers. So out of all of this, the key point I want to make is, if r is between -1 and 1, then we can look at the sum to infinity. And then it's going to converge is the word that we use. So it's going to get like, I don't know, it's going to get smaller and smaller, closer to an answer. Right, so let's look. Sum to infinity, we still don't have a nice formula for it. We have an idea of what it might mean, that we're keeping on adding forever and ever, and we're going to get closer to an answer. So here's our sum formula. Now a is going to be our starting term. That feels like it's going to be fixed. 1 minus r, that seems like it'll be fixed. If r is a half, it'll be like 1 minus a half. But let's look at this top part here. 1 minus r to the n. What is r to the n going to look like when n gets like really, really big and r is a fraction, like between 0 and 1? Calculator time. Let's really like look at it here. Let's look at our calculator. So let's take that half. So I'm going to write 1/2. Now let's say we square it. We get a quarter. What happens if we take it to something bigger, like a 5? 1/32. Bigger or smaller number? Well, it's a smaller number than we had before. What about to the 10? Or 10. Do you think this is going to be getting smaller or getting bigger? Well, it's getting a whole lot smaller. Look at that. It's let's turn that into a decimal that we can make sense of. Look at that, 0,0009 as a fraction 1 over 1024. This is getting smaller and smaller. So what happens if we had like to some huge number? Well, as it gets bigger, a half to like a really, really big number is going to get closer and closer to 0. Now, when we looked at that in exponential functions, our exponential functions did that, and we had an asymptote, and I don't want to overthink it. But the point is, this number is going to get closer and closer to 0. So, this part here, so that r to the n is going to get closer and closer to 0, which means 1 minus 0 is 1. So it looks like it's going to be a 1 minus 0, which is just 1 over 1 minus r. Oh, but a times 1 is just a. So after all of that, our new formula, S infinity, is a over 1 minus r, when r is between minus 1 and 1. Because it needs the ratio that needs to be a converging sequence. Pause, let it settle. Let's look at a few examples where we just apply our formula. We're given a geometric progression, 16 plus 8 plus 4 plus forever. The sum to infinity. So if we kept doing this forever and a bit more, what is our answer? How are we going to work it out, and what is our answer? Well, the way I would work it out is to write a really bad infinity and go, well, I know the formula is a over 1 minus r. I know the value of a, 16, 1 minus value of r. Now be careful, it's halving, right? So if we're halving, our ratio must be a half, because our ratio is 8 over 16. 8 over 16. Cool, which is just a half. So 1 minus a half. Calculate if you really want to, I don't think it's necessary. 1 minus a half is a half, 16 divided by a half is 32. Cool. So that was that, not too bad. Example 2. Determine the values of k such that this sequence given converges. So it's a geometric progression. So if it converges, if a sequence converges, what do we know the ratio must be? Between which two numbers must the ratio be? Well, it needs to be between -1 and 1. So if our ratio is between -1 and 1, then we know it converges. In other words, in our examples we looked at above, we don't want this type of thing going on here with, and I should point up that we don't want that top one going because it's not converging, it's getting bigger and bigger and bigger. We don't want the second one because it's also getting kind of bigger and bigger and bigger. But we want like this one and this one where it's getting convergent, right? It's getting closer together. So if something converges, the ratio must be between -1 and 1. Okay, so how do we work out the ratio of a geometric progression? Well, we just take this second term and divide it by the first term. So our ratio is 8k squared over 16k. Well, 8 over 16, that's a half. K squared over k, well, that's k. We said that r needs to be between -1 and 1. Let's just times everything here by 2, so we get k. And k must be between -2 and 2. But the key part, this was our key part here. R needs to be between -1 and 1 for the sequence to converge. Okay, last piece of the puzzle. Determine S infinity. So determine the sum of the sequence to infinity if k equals -1. S infinity equals a over 1 minus r. A and r. That's all we need to know. A, 16k. Okay, but k is -1. So what is the value of a if k is -1? Well, it's just minus 16, right? Okay, what about r? R, we said, was a half k. So if r is a half k, and k is -1, what's the value of r? Well, it's just -1/2. Cool, so sub into the formula, minus 16 over 1 minus -1/2. Right, that was our ratio, wasn't it? -1/2 equals, well, minus 16 over 1.5 gives us what? Is it about 12 or so? Let's just use our calculator to check. So we've got minus 16 over 1 minus half minus 32 over 3. Well, that's minus 32 over 3. No, so not a nice neat number, but there it is. That's it. Enjoy the exercise. Let's remove that calculator so you can see question 2 and 3, because those will be good juicy ones that you'll enjoy, I'm sure. Enjoy, and enjoy the weekend.